Hello friends, myself Dr. Nandakumar Raubale from College of Engineering Ambazugai is going to deal with Applied Thermodynamics 1. This is our 30th lecture. In previous lecture, we have discussed numerical on gas power cycle, that is on Stirling cycle. So today we will discuss a numerical on Brayton cycle. So here there is one problem. A gas turbine works on an air standard Brayton cycle. The initial condition of the air is 25 degrees Celsius and 1 bar. So temperature T1 is 25 degrees Celsius and pressure P1 is 1 bar. The maximum pressure and temperature are limited to 3 bar. Maximum pressure is limited to 3 bar P2 and maximum temperature is limited to 650 degrees Celsius, that is T3 is equal to 650 degrees Celsius. Determine the following. So we have to find out cycle efficiency, heat supplied and heat rejected per kg of air, work output per kg of air, and exhaust temperature. So looking at this diagram, so what is given? The initial temperature is 25 degrees Celsius and pressure is 1 bar. So here it is given pressure is 1 bar, temperature is 25 degrees Celsius. So here T1 is 25 degrees Celsius, whereas pressure P1 is equal to 1 bar. And then next condition given is the maximum pressure and maximum temperature are limited to 3 bar and 650 degrees Celsius. Maximum pressure is 3 bar. So P2 is maximum pressure, which is 3 bar. So here we can assume that P2 is equal to P3 and is equal to 2 bar. Both are at maximum level. So pressure at point 2 is equal to pressure at point 3. Therefore, we can write P2 is equal to P3 is equal to, sorry, not 2 bar, it may be 3 bar. It is 3 bar. So this is 3 bar. And here initial pressure is given as 1 bar. So P1 pressure at P1 and pressure at point 4 are same because it is constant pressure process. So we can write here P1 is equal to P4 is equal to 1 bar. One more condition is given. The maximum temperature is 650 degrees Celsius. So maximum temperature is 650 degrees Celsius. So on TS diagram, if we see, so the point T3 is at the highest distance from x-axis. So that is temperature at point 3 is 650 degrees Celsius. Now he is asking us to find out cycle efficiency, heat supplied, heat rejected, work output per kg of air, and exhaust temperature. So let us collect this data. So already it is given in this problem that initial pressure is 1 bar and initial temperature is 25 degrees Celsius. So 25 degrees Celsius means in degree Kelvin, 25 degrees Celsius plus 273, this works out to be 298 degree Kelvin. Then the highest pressure P2 is equal to P3 is equal to 3 bar, which just we have seen in this previous diagram. P2 is equal to P3 is equal to 3 bar, and initial pressure P1 is equal to P4 is equal to 1 bar. Then highest temperature is given as 650 degrees Celsius. So 650 plus 273 is the highest temperature in degree Kelvin. So therefore, the highest temperature is 923 degree Kelvin. Okay, this is temperature T3, highest temperature. So then he is asking us to find out cycle efficiency, heat supplied, heat rejected, work output, and exhaust temperature. Exhaust temperature means the temperature at last point. Say this is 4 at point 4. What is the temperature at point 4? That is asked here. So now find out cycle efficiency. Cycle efficiency is equal to work done into 100 divided by heat supplied. Work done is obtained by heat supplied minus heat rejected. Once we know heat supplied, we know heat rejected, then we can find out work done. So to find out heat supplied during process 2 to 3. So if we see heat is supplied during process 2 to 3, Q in. So heat supplied during constant pressure process is given by M Cp delta T. So here M we are going to assume as 1 kg of air. So therefore we do not consider this M. So Cp into delta T. Delta T means change in temperature, T3 minus T2. So this will give us the value of heat supplied. So now coming to this heat supplied, M is equal to 1, Cp is known, then T3 temperature at point 3 is 923 degree Kelvin and temperature at point 2 we have to calculate. So temperature at point 2 can be obtained by using PVT relations, and that PVT relation is given as T2 divided by T1 is equal to P2 divided by P1 into to the power of 1 minus gamma 1 minus 1 by gamma. So from this we can find out T2. We know T1 is known, P2 is known, P1 is known, gamma is 1.4. So from this we can find out T2, and by substituting T2 in this above equation we can get heat supply. Then after this we want to find out QR, heat rejected. So heat rejected can be obtained as Cp T4 minus T1. So coming back to this 4 to 1 process, heat is rejected. So again 4 to 1 process is constant pressure process. So heat supplied during constant pressure process is again given by MCP delta T. M is taken as 1. Cp is specific heat at constant pressure for air, and delta T is change in temperature from 4 to 1. So T1 minus T4 minus T1 is the change in temperature. So here T4 is not known. T1 is already given in this problem. Temperature T1 is known to us, that is 298 degree Kelvin. Then T4 can be obtained by using PVT relations, T4 divided by T3, applying the PVT relations for process 4 to 3, 4, 3, 3, 4. We can get this relation T4 divided by T3 is equal to P4 divided by P2 to the power of 1 minus gamma. 1 minus 1 by gamma. So this gives us T4. From this T4 we can find out heat rejected. Heat rejected is known, heat supplied is known, then work done can be obtained. So work done is known, heat supplied is known, cycle efficiency can be obtained. So this same cycle efficiency is given by another formula, that is 1 minus 1 divided by Rp, where Rp is the pressure ratio to the power of 1 minus of 1 by gamma. So where Rp is equal to pressure P2 divided by P1. So now we'll start to find out the values of various things which we have to find out: heat supplied, then heat rejected. So prior to solution, first we'll start with the values of T2 and T4. We'll find out first. First we'll take down these two equations for simplification of a problem. T2 divided by T1. T2 divided by P1 is equal to P2 divided by P1 to the power of 1 minus 1 by gamma, or this can be written as P2 divided by P1 to the power of gamma minus 1 divided by gamma. So from this we can find out the value of T2. Temperature T2 is equal to T1 into P2 divided by P1 to the power of gamma minus 1 divided by gamma. The temperature T1 is known in degree Kelvin, that is 298 degree Kelvin. 298 degree Kelvin is T1. So 298 into P2 is 3 bar, P1 is 1 bar, to the power of gamma value is 1.4 minus 1 divided by 1.4. On simplification we will get this as e to the power of 4 by 1.4 to 98. So this temperature T2 works out to be 407.88 degree Kelvin. So this is temperature at point 2 we obtained. Now coming back to another equation to find out T4 divided by T3. T4 divided by T3 is equal to P4 divided by P2. P4 divided by P2 to the power of gamma minus 1 divided by gamma. P4 divided by T3 is equal to P4 divided by P2 to the power of gamma minus 1 divided by gamma. So now T4 is equal to P3 into P4 divided by P2 to the power of gamma minus 1 divided by gamma. Temperature T3 is given as 923 degree Kelvin. 923 degree Kelvin into P4. Pressure at 4 is equal to 1 bar. The pressure at point 2 is equal to 3 bar to the power of 1.4 minus 1 divided by 1.4 bracket close. On simplification we get this as 674.34 degree Kelvin. So we know T2 as 407.88 degree Kelvin, just we have obtained, and T4 is equal to 674.34 degree Kelvin. Now we'll find out heat supplied. The heat supplied is given as Qs is equal to Cp T3 minus T2. Heat supplied is equal to Cp into T3 minus T2. So Cp value is 1.005 into T3, temperature 3 is 650 degrees Celsius, or that is 923 degree Kelvin, 923 minus T2, temperature 2 is 407.88, 407.88 degree Kelvin. So this gives us heat supplied per kg in kilojoules per kg. So this can be 923 minus 407.88 into 1.005. So this is 517. 517.69 kilojoules per kg air is the heat supplied. US heat supplied is octet. Heat supplied during process 2 to 3. Now heat rejected during process 4 to 1. We can write it as QR is equal to Cp T4 minus T1. T4 minus T1. Cp value is 1.005. T4 temperature at point 4, just we have calculated as 674 degree Kelvin, 674.34. 674.34 minus of T1, temperature T1 is 298 degree Kelvin, 298 degree Kelvin. So this gives us heat rejected 1.005 into 674.34 minus 298, 378.22 kilojoules per kg. So this is how heat rejected is obtained. Therefore, work done per kg of air is equal to heat supplied minus heat rejected. So heat supplied is known, that is 517.69 minus heat rejected is 378.22. So therefore, the work done per kilojoule of air is 517.69 minus 378.22 gives us 139.47 kilojoules per kg. So this is the work done. Now to find out efficiency, so efficiency of cycle is equal to work done divided by heat supplied into 100. So work done, just we have calculated as 139.47. 139.47 divided by heat supplied. Just we have calculated heat supplied as 517.69. 517.69 into 100. So this is equal to, divided by 517.69 26.94% is the efficiency. So next, what is asked in this problem, we will see. Here we have obtained cycle efficiency, heat supplied, heat rejected, work output, exhaust temperature also is known, that is temperature T4. So there is another way to find out cycle efficiency using this formula. So we will try to find out cycle efficiency using this pressure ratio formula. Cycle efficiency is given by 1 minus 1 divided by Rp to the power of, just coming back, 1 divided by Rp to the power of 1 minus gamma by 1, or gamma minus 1 divided by gamma. So pressure ratio Rp is equal to P2 divided by P1. So we'll see here P2 divided by P1. So P2 divided by P1, P2 is 3 bar, P1 is 1 bar. So pressure ratio is 3. Therefore, 1 minus 1 divided by 3 to the power of 1.4 minus 1 divided by 1.4. This gives us efficiency of cycle by another method. This is 1 divided by 3 power of 3.4 divided by 1 minus 1. So by this method also we are getting efficiency as 26.94%. So this, if we multiply it by 100, then it will be in percentage. So by both the methods we obtained same answer. Now just we'll have the summary. In this summary we will find out heat supplied QS is equal to 517.69 kilojoules per kg. Then heat rejected QR is equal to 378.22 kilojoules per kg. Then work done is equal to 139.47 kilojoules per kg. And exhaust temperature at 0.4 T4 is 674.34. 674.34 degree Kelvin. These are the things which were asked. Find efficiency of cycle, which is 26.94%. So these are the things which were asked to us to find out. So with this we have completed third unit, where we have studied steam cycles as well as air standard cycles, and we have seen some of the numericals on this. So today we have covered third unit of your syllabus. So we will start with the fourth unit in next lecture. Thank you.